Good afternoon, everybody, and welcome to the Masters in Engineering Bursary Program brought to you by the Paper Manufacturers Association of South Africa. I just want to give some welcomes to Jane Maloney, the Executive Director of PAMSA, Normali Msimanga, she will be presenting first, after that Chris Denton. And then, of course, we have Julie Borland, who is the engine room of the Masters program. So we just give her thanks for all the work she does in terms of guiding the students through their programs, but also to the various universities and all the work they do. And of course, our members who sponsor many of the bursaries for these students. So without further ado, I'm going to ask Jane to give her opening remarks.
Thanks very much, Samantha. This is always a really, really good time of year and something that we look forward to, the Student Annual Review. It's exciting to know that we have had probably around 100 students that have been where you two are right now. Of course, when they started back in 2008, we didn't have online meetings like this. They had to present in person. And so I don't know whether you guys have an advantage or a disadvantage. You tell me. At least you are sitting in the comfort of your own office or your own home. You haven't had to get on an aeroplane and fly to Johannesburg. And in fact, we are all in our own spaces. So it's quite remarkable how things have changed. And we see that change in our sector. One of the exciting things, I've just come back from the Gold Pack Awards, and paper rules supreme. As plastic is under a lot of attack, I'll put it like that, and not all the facts about plastic are correct, we are seeing more and more substitution. And we're seeing more and more demand for packaging to appear as if it's behaved like plastic, which means we need more and more water-soluble solutions. We need the extra strength that we can give to packaging from nanocellulose or whatever other opportunities you have. And as always, we need to know how to use the entire tree, which is why what you two have done is so important. And it is the work that people like yourselves do that keeps our sector thriving. So I want to encourage you. I hope that you do stay in the sector when all is finished and done, because it's a wonderful sector to be part of. It's renewable, it's circular, and it's a brilliant example of the circular bioeconomy. So without further ado, I'll hand back to Samantha and enjoy. I'm sorry that I won't be able to stay for the entire time. Thanks.
Thank you, Jane. Yeah, I think you've summarized the value that this program adds to our industry and the number of students that it is sort of aided through the number of years that it has been running. I am going to introduce Normali Msimanga. She has the pleasure of being first. Normali is going to be presenting the development and evaluation of a data-driven model for a kraft digester. She is from the University of Witwatersrand, and I am going to give her the microphone and the floor.
Thank you, Samantha, for a lovely introduction. Good day, ladies and gentlemen, and my name is Normali. And first of all, I would like to thank PAMSA for this lovely opportunity, and Mondi for giving me support throughout the research. My research is based on the development and the evaluation of data-driven model of a continuous digester. Then the reason why I chose this research is mainly because of my interest in machine learning and data science. And I wanted a research where I could incorporate my passion for chemical engineer, because I am a chemical engineer, and also infuse that with my interest in data science. And I believe that this research has allowed me to do so. The paper industry finds itself in a very competitive market, and this is mainly due to the availability of different products. Hence, the need to improve pulp quality and optimize the process is of essence. And this is to make sure that companies take a full advantage of the competition and making sure that they produce high quality products. The aim of this research is to develop a data-driven model, in short, a soft sensor, that will be for a continuous digester. So this model will allow operators to predict the different pulp quality variables and be able to look into the performance of the digester. So this model will take in a few inputs, and it will give out a predicted output. Using this model, operators will be able to monitor, optimize, and control the system. So you find that when there are certain things that are happening in the process, operators will be able to predict what is the outcome quality of the pulp that they produce based on the changes that happened in the input variables. So they do not have to wait for 8 hours to be able to see what will be the outcome. And they can also optimize the process by looking by using the model to fiddle around and finding the optimal states or optimal conditions for their desired target quality of the pulp. This model can also be used in process fault detection and online analyzers fault detection. So in case where there is a high drift between the predicted output and the actual value that was obtained by an online analyzer, operators will be alerted and they can go and look into the process to check what is really the problem. So this model will be predicting different variables, for example, yield, which is the amount of pulp that is produced per amount of wood that is fed into the system. And then we also have the kappa number, which is the amount of lignin in the pulp. So the main aim of cooking the wood is to remove the lignin. So by looking into the lignin amount that is in the pulp, it is just to check how good of quality is the pulp. And then we have a production rate, and production rate is the amount of pulp that is produced per a given period. And lastly, H factor, which is a constant that combines the reaction time and temperature. So this factor allows us to see the extent of the cooking process and be able to tell how good is the pulp or how good is the reaction that happened within a digester. The first model is the kappa number. And the kappa number, the inputs that were used in the kappa number model were the white liquor active alkali, bottom extraction temperature, top separator level control, and bottom extraction effective alkali. And this inputs really assisted in making sure that we capture the relationship and being able to predict the accurate kappa number, because as you can see on your screen, this is a time series, and the orange dots represents the orange dot represents the predicted kappa number, and the black solid line represents the values obtained in the plant. So if we can look, the value orange dots, they are along the black solid line. And this shows that the model is able to capture the relationship between the input and the output, and it gave accurate values of the kappa number. And this is further accentuated by the correlation graph, which shows the correlation between the actual value of the kappa number and the predicted values from the model. And the blue solid lines, the blue points, they are clustered together towards the black solid line, which is the ideal model. And the more closer they are to the ideal model, this shows how good the model is. Another model, we have a wood to pulp yield model. And in this model, only one input was used, which is the digester top pressure. And using only one input for this model really and to see such powerful results and how the model performs is really an amazing thing, because if you look at the orange solid lines, they are along the orange dots, they are along the black solid line. And this shows that the model can predict reliable results of the yield. And if we look at the correlation, the points are closer towards the black solid line. And when we go to the production rate model, for the production rate, in the prediction of the production rate, the chip feed, bottom extraction, effective alkali, and impregnation vessel temperature were used as inputs. And one thing that is different from this model is that the production rate itself is a variable that takes finite values. This means that operators, they set it to certain values, and hence why you find the time series is different from the other models. But even though this model is good, by looking at the orange dots that are along the black solid line, but then you find some areas that are circled by a red circle, and that's where the model kind of underestimates and overestimates. So, and this can further be seen in the correlation matrix, where some of the points, they are far away from the black solid line. And the reason why, again, this correlation is different from the other models is because of the discreteness of the production rate variable. Going to the H vector model, the white liquor, effective alkali, bottom extraction temperature, top separator level control, bottom extraction effective alkali, and impregnation vessel liquid to wood ratio were used as inputs to this model. And same as the H vector model, this model is good, but then at lower ranges and high ranges, we can see that the model is overestimating and underestimating some of the values, because the orange dots, they are above the black solid line. And we can also see that in the correlation, because the points are far away from the black solid line in the lower ranges of the H vector, and they are below the black solid line in the higher ranges of the H vector. And this model, even though it shows potential, it is good, but it is not well. So it still needs some improvement to it. And in conclusion, the model can predict reliable outputs that will assist in monitoring the performance of the mill. It can also generalize well. So this means that it can adapt to new and unseen data, because the data that I've shown you is from the testing results. So the model was trained, validated, and tested. And the model have also shown potential to be used as optimizing, controlling, and monitoring tool. It can also be used as fault detection, and more work still needs to be done to validate its effectiveness to this application. Thank you.
Thank you, Nomali. That's great. Thank you so much for all of the work that you're doing. I think it goes a little bit over my head. So you've got a round of applause there from many people. I want to open the floor for people to give their questions or present their questions. Perhaps if you wish to raise your hand, and then I can make sure we keep an order of who will unmute their microphones. Bernadine, you are welcome to ask your question.
Yes, so thanks so much for your presentation. Quick question. So what will the next steps be to improve some of these models for some of the factors that you looked at? Because especially on the H factor one, it's you need to do improvement there. So what will your steps be to do that? Because you're under predicting high and over predicting low. So what's the plan there?
So the plan is to, because at this moment, but then I think it can be improved by looking into putting the other inputs into it, because the model might be lacking in terms of the inputs, so it can't really describe what is really happening in the lower ranges and higher ranges. So if maybe can look into putting more information and training it on that more information, then the model might improve.
Thanks.
Thanks, Bernadine. Another question, I think, is Clinton Govender.
Thanks very much, Sam. So, Nomali, thanks very much for that interesting presentation. I just want to check. You can have different behavior of kappa number for different types of digestive systems. So you can have like here in Richards Bay at the Mondi Mill, you have low solid cooking. You might have a different type of cooking technology in a different mill. How would you, is this specific for a specific type of cooking mode or technology? You weren't very specific in your presentation on the cooking modes and the cooking technology. How would you adapt your model for different cooking modes in different mills?
I think the research is based on the Richards Bay model, the continuous digester. They are continuous digester. But then when it comes to implementing it maybe to different technologies of the mill, I think it can still be implemented, but it still has to be validated, because I didn't really go into detail to check if it can be used at different technologies. So when we have different technologies rather than the Mondi's technology. So I think still need to validate and check and to make sure that it's suitable for the other digesters, not just the one that I used to model the kappa number.
Okay.
Okay, we have a question from Madimecha, and then we have a question from Ralph, and then we have a question from Kevin Brooks. So Madimecha, you are welcome to ask your question.
Hi, Nomali.
Hi.
There's a part where you indicated that the model can also be applied for fault detection. So I have two questions. The first one is that, did you use both the nominal and faulty data in the model training?
Did I use both the?
The nominal and faulty data in the model training stage?
No, I didn't. So initially, I filtered out the values that that are out of range and where there are spikes in the data, just to make sure that the model is accurate. But then when it comes to fault detection, I used another technique to look into the squared prediction errors and making sure that the error between the actual and the predicted, if it is at the certain range, then you can identify a point as a fault, or if it is not, then it's not a fault. Yes. I don't know if I have answered your question.
Okay, then for the faulty scenarios, I wanted to ask, because there are different types of faults that can occur within the pulper digester. So I wanted to ask that if you took into account the different type of faults, whether it's channeling or hang up or screen clogging, and how that affected the different input variables. Because you find that perhaps, let's say, if you were to look at channeling, this one affects a particular input variable but does not affect another one. And in that particular order.
Okay. So what I validated was just detection of the fault, but then not diagnosis of the fault. So for now, it can detect whether there is something wrong in the mill or a process, but then it can't actually pick up where exactly is the fault. So yeah.
Okay, so you mean the detection in terms of the output value?
Yes.
Okay.
Yes.
Thank you.
Thank you so much. Ralph, you're up next for your question.
Thanks, Samantha. First of all, well done, Nomali.
Thank you, Ralph.
I think the question that I have is maybe similar to what Dean asked, and that is, I can understand that we need to do more work with regards to the over and the undercompensating, but do we understand why? Why for the lower values are we overcompensating on the module, and for the higher values or predictions it then undercompensates? Do we have an understanding of why it does that?
I didn't get into that or like be able to pick up why exactly was the reason why we are overestimating at lower ranges and underestimating at higher ranges. But I think it's a matter of the model itself, because the model that I'm using is just I'm feeding in data, so I don't really know how did the model pick up the relationship itself. So my understanding would be it's because maybe I didn't put in an important variable into the model, and maybe by putting that variable, then that overestimating and underestimating might be overcome. Even though I tried different ways and I tried different techniques when it comes to the H factor, and maybe trying to combine a random forest with another machine learning to kind of improve the performance of the model. But this is where I am right now and what I have.
Okay. All right, I'm happy for my side. Thank you, Nomali.
Thank you, Ralph.
Thanks, Ralph. Kevin, you're up next.
Yeah, thanks very much. I should declare that I'm one of Nomali's supervisors for her thesis. So partly to answer Ralph's question is Nomali's quite correct. There appears to be some missing input. And the thing that we're probably missing is some characteristics of the feed, something about the wood, perhaps. That's not measured, so it's not in the model. But the other thing I wanted to just confirm with Nomali is these models are not linear regressions. These are machine learning models that are inherently nonlinear. So I think just to confirm that they are, in a sense, much more sophisticated than what we could do maybe, I don't know, 10 years ago, 20 years ago. So Nomali hasn't talked, because it's fairly technical, hasn't talked about the actual algorithms used, but just to confirm that these are inherently nonlinear models. And if you try to do the linear modeling of these sort of systems, you just don't get very good models at all. So sorry, Nomali, it's a statement rather than a question, but you may want to back that up.
Yes. So I in the analysis and being able to pick up which model I used, I also included the linear regression just to make sure that maybe the linear regression will perform better than the nonlinear regression, better than the nonlinear models. So in that analysis, and we realized that the random forest is the one that gives us the optimal results and captures the relationship between the output and the input very, very well. So hence why Kevin mentioned that we used the nonlinear instead of the linear models.
Thanks, Nomali. And then we have a question from Busani.
Thank you very much. Thank you very much for the presentation. Nomali, very much appreciated. I just wanted to check Nomali, and I think I missed some of the information there. But for me, I'm not asking questions today, but probably I'll ask my questions via the email directly to you after. I mean, I've basically got time to basically look. More interested in your input. Can you please share again what were your inputs on your kappa model? So then I probably will be able to analyze or probably share our understanding of how our research beta is performing at the moment, and then can be able to probably add more input into your research and also the behavior of your model based on the practical experience or historical experience that we have accumulated over the past, I would say now 20 years of this continuous digester. Will you be able to share that with us, or maybe with Ralph? Then we can take it from Ralph, maybe, so I don't waste time in the meeting. But otherwise, very much insightful.
Thank you. Just to, I don't know, maybe that will require us to talk through email. And thank you for the offer. But what I used for the kappa number, and this is not just me pick and choosing whichever variable that I want. So there was a certain model that looked into the correlation of the kappa number and a whole lot of variables. They were around 30 something. And from those variables, I looked at the correlation and chose the top 10 or top 9 that were correlating with the kappa number. And in those variables, I also used a VIF, which is a variance inflation factor. So basically what this is, it just takes each variable and trying to predict. So it takes certain all the top variables and then predicting the outcome of one variable out of all these other variables. So it was just to check and making sure that my variables, they don't they do not have I don't have a multi-collinearity within the variance. So because if you have input variables that have relationship with each other, they can reduce the accuracy of the model. So from that analysis and that model of selecting the input variables, the white liquor active alkali, bottom extraction temperature, and top separator level control, and the bottom extraction effective alkali were the top variables that came out of that analysis.
No, that is great. Thank you. That is enough. Yeah. So I think I will share the other questions probably with you on email.
Thank you so much.
Thank you, Nomali, for answering those questions so well. If you do have more questions for Nomali, you can put them in the chat a bit later if you think of something. But I'd like to now hand over to Christopher Denton. He is going to talk about acetylated nanocellulose as a reinforcement for cellulose acetate. He is from the University of Pretoria. So I'd like to introduce him, and yeah, we'll hand over the mic.
Thank you very much, Samantha. Good afternoon, everybody. My name is Christopher Denton. I'm a master's student at the University of Pretoria, and today I'm going to be telling you about my research, which is acetylated nanocellulose as a reinforcement for cellulose acetate. I'd just like to take a moment to say a huge thank you to PAMSA and by an extent SAPI for giving me this opportunity. I've always been passionate for the renewable sector, and I've always believed that as the world moves towards a circular economy, there will always be the need for innovation and development. Firstly, a bit of background on nanocellulose. It is the highly refined tree pulp, and it mainly comes in three forms, namely cellulose nanofibers, cellulose nanocrystals, and bacterial cellulose. My interest is on cellulose nanofibers, and what makes them special is that they have an incredibly high aspect ratio. So where the fiber diameter can be 5 to 100 nanometers long, the actual length of the fibers will be several micrometers. This means it has an extremely shear thinning capability, which means if you were to apply a force to it, it will flow and move like a liquid. However, if you remove that force, it stiffens up and behaves like a solid. This makes it extremely useful for things like pumping concrete, where you need to pump your cement up to a high level, but don't want it to slip through the cracks, as well as in other things such as beauty products, where you want to rub a moisturizer around your face, but you don't want it to slip off. It also has many other applications in coatings and other paints. This is one factor, but there is also the other reinforcement capability, as we know, with cellulose being quite a strong biodegradable fiber. If you remember a student from last year by the name of Zion Hook, he did some great work into the drying of the cellulose nanofiber, and he also did a synopsis into the reinforcement of it in thermoplastic starch. Now, with thermoplastic starch and cellulose nanofibers, they have a very similar molecular makeup. The only difference is that starch has a swapped glycosidic bond. This means that when you mix the two together, you get a very nice distribution of the fiber throughout your matrix. However, I challenged myself and went with cellulose acetate, which has an acetyl group, which means that cellulose nanofibers and cellulose acetate do not like each other. This leads to a problem known as hornification, where the cellulose nanofibers would rather stick to themselves than distribute evenly throughout the film. And as you can see in the bottom left of your screen, this is what happens when you mix the two together. You also get what's a phase inversion, which destroys the transparency of cellulose acetate, because cellulose nanofibers are water soluble and cellulose acetate is not. So this leads to a terrible film with also lots of bubbles and other bad properties. So to clarify down to the objectives of my research, I want to demonstrate that cellulose nanofibers can be used as a reinforcement in biodegradable plastics, similarly to the way glass is used, fiberglass is used for its reinforcement capabilities. Glass has some of the highest tensile strengths, however, it is not biodegradable, and in some cases where you do not want all that strength, but you still want your plastic to be biodegradable, I believe that there is a space for cellulose nanofibers. The way I would want to incorporate it is through the improved dispersion of the nanofibers into the matrix, and also while maintaining the chain lengths of the nanofibers, which is what they are known for. All of us also want the byproduct of the cellulose acetate film remaining some sort of transparency. The planned solution was to use acetylation of the nanofibers to improve the dispersion in the matrix. On the right of your screen, you'll see a monomer for cellulose nanofibers. This molecule has 3 hydroxyl groups. These groups can be easily acetylated. Acetylation is the process of essentially removing a hydrogen from one of the hydroxyl groups and replacing it with an acetyl group. This will improve the attraction of the cellulose nanofibers to the cellulose acetate matrix and improve the dispersion. The main concern with this process is that the acetic anhydride used in this acetylation can attack the oxygen bond in the chain, which can really lead to the cellulose nanofibers becoming cellulose nanocrystals. There were 4 different degrees of substitution for the testing. The degree of substitution simply relates to, out of the 3 available hydroxyl groups, how many were acetylated. In this case, on the right is a DS of 1. The other DSs used in testing were a DS of 0 for a control, 0.5, and 1.5. Each one of those degrees of substitution had 4 different concentrations of cellulose nanofiber, namely 2%, 5%, 10%, and 15%. The acetylation was confirmed using Fourier transform infrared. This machine essentially measures the concentration of the double bonded oxygen in your substance or film in this case. And due to the fact that the oxygen double bond is unique to the acetyl group, the concentration, and in this case, the degree of substitution, can be confirmed through FTIR. And as you can see at the bottom of the screen there, this acetylation led to a much clearer, more even film. Turning towards the results of this, I'll turn on my laser pointer to make it clearer. Looking at the FTIR spectra of the graph, we can see that with an increase in DS, we can see an increase in this wavelength. This wavelength corresponds to the double bonded oxygen group. It is slight, but we do not want to go overboard with the acetylation, as it will lead to the chain being cut up. In order to use this FTIR data quantitatively, we need to use a reference point, something that is common across all samples. In this case, the oxygen bound in the ring, which I believe has a wavelength of around 1100, is used as the reference point, which leads to the DSs being comparable to each other. Moving on to the modulus of elasticity and tensile strength. The modulus of elasticity essentially refers to how tough the plastic is and how much energy it can absorb before it breaks. Comparing a neat cellulose acetate with the other DS samples, all of these DS samples contain a 10% concentration of cellulose nanofibers. And we can see that by adding an unacetylated cellulose nanofibers, we have an increase of around 100 megapascals in our film. However, by simply acetylating the nanocellulose to 0.5 DS, we get more than twice the jump, up to 1,000 megapascals, in the modulus of elasticity. This is a huge improvement, and essentially for the same amount of material that you've added to your film, you've more than doubled the outcome of it. There was also an improvement into the tensile strength of the films. However, due to cellulose acetate already being a fairly tough, strong plastic, it does not hugely affect it. And as you can see from the slide earlier, there was a great increase in the transparency of the films. Moving on to the fiber agglomeration, which refers to the fibers attracting to each other. This was checked using TEM, transmission electron microscopy, and light microscopy. TEM was used at a scale of around 100 to 200 nanometers, which really allowed to see down deep into the fibers to see what was happening when the agglomeration occurred. And it could be seen in these TEM samples that the acetylation allowed the fibers to push away from each other more and be more dispersed. However, I prefer to show you the light microscopy samples over here. These are taken of a 15% cellulose acetate film with 15% cellulose nanofiber at 1,000 times zoom. So the scale over here is around 10 micrometers in the bottom. And we can see that without acetylation, these fibers will group together and form these big bundles like over here. This bundle is around several micrometers in diameter. So going from our cellulose nanofiber, which typically has a diameter of 100 nanometers, we've drastically increased that to 100-fold. Whereas when we compare this to our acetylated version on the right with a DS of 1.5, the fibers are still present in it, but they are much smaller. This means that for the same amount of cellulose nanofibers, we are getting more fiber distribution throughout the plastic and more chance for them to absorb energy. Moving on to the conclusions, it has been shown that the cellulose nanofibers can be used as a biodegradable fiber reinforcement in cellulose acetate. This was done through the improved dispersion of the nanofiber while maintaining the chain length of the nanofiber. It is also important to note that the addition of the nanofiber does not in any way harm the biodegradability of the cellulose acetate, since it is essentially adding paper to plastic. When it comes to the uses of this research, it must be noted that all this testing was done for solvent cast films of cellulose acetate. However, it is just as viable in other production methods such as extrusions and injection molding. The film still maintains all of its qualities as it were, with a slight decrease in the optical transparency, but still remains food safe. The last point that I want to touch on is that this research is not solely for cellulose acetate polymer. it can be also extended to other similar biodegradable plastics like polybutylene succinate and other polyhydroxyl alkanoates. So thank you very much.
Thank you, Chris. I'm glad, well, I'm grateful to nanocellulose that my moisturizer doesn't slide off my face. So yes, so if you're getting another, or you're getting a round of applause too, I want to open the floor to any questions from our audience. Bernadine, you can ask your question.
Thank you so much. Christopher, thanks for your presentation. Very interesting. Just a quick question. What was the source of your nanocellulose?
Sappy Velida.
Oh, Sappy Velida. Okay. And you sure it did fall within the nano range?
Yes, yes. This was also characterized by Zion Hook.
Okay, okay, good. Thanks.
Thank you.
Any other hands? I don't see any. We got one from Mr. Dutoit.
Good afternoon. Thank you so much for your presentation. I just wanted to ask, in addition to checking the degree of substitution, did you also evaluate the impact of the regioselectivity?
Sorry, the what?
The regioselectivity. So where does the acetylation actually occur? On which hydroxyl group? Does it have an impact?
No, I don't believe it has an impact. And from research, the acetylation is mainly happening on the surface hydroxyl groups of the fiber chains.
Thanks, Chris. I hope that answered Mr. Dutoit's question. I am not seeing any more hands, so yeah, I don't see any more hands. So I think, Chris, you're off the hook.
Thank you very much.
So yeah, thank you both for your presentations, and again, thank you for all the work you put in. I can't even imagine what it must be like to be a master's in engineering student. So I want to hand over, I believe, is it Ralph who's going to be doing our closing remarks?
Right. I hope the audio is still good. So thanks for that, Samantha. So yeah, just by way of introduction, I'm Ralph Niebuhr, the L&D manager for Mondi. So I was asked by Julie just to have some closing comments with regards to the master's program. Since we started with the process and current state of it. So it was introduced many, many years ago. So I don't want to give away the age, but we have introduced it for a couple of years ago, and we've seen some great successes with it. So from that, we obviously on the industry side, it's twofold. One is the value that we gain from the insights of the research that was done. And secondary then is the value that we gain from the candidates that enter the industry. So from the Mondi side and so forth, we've seen some great successes from master students that have completed their 2 years of studies and then enter our processes with regards to becoming good and future process engineers. So that is always two folds of benefits to this process. Then I would also like to take an opportunity to thank the industry partners. In other words, research is depending on information that they obtain from industry. So from our industry partners, whatever you supply them with is the appreciation of the information shared, because that is what they use for the research that is completed. So thank you for that as well. And then also on the panel members that are available today with regards to listening in on the presentations and then being able to table some questions. Thank you for that. And then last but not all, on the two candidates that presented today, I think I'm not the subject matter expert with regards to content, but the effort of a year and a half research done thus far, the progress that you have presented thus far, the preparation to the presentations, I think must have been pretty darn good, because you presented quite comfortably. And with being able to answer some of the questions, it is that you know what you're talking about. So well done on that, and keep it up. So you guys are in the last stint of your process, so you will be going towards your final thesis submission and write-up, so good luck with that. And then, yeah, all the best. And Nomali, I'll see you next year. Thank you.